university courses in Bolivia, there is no dedicated biomechanics labs. Measurements are done with limited resources or with improvised images or without a standardized capture protocol. This introduces variability or makes comparisons difficult and weakens learning. BioTrack was created to solve this problem from an educational perspective. It is a system that standardizes the capture before measuring. The user enters their height and selects the joint to be evaluated. Based on the anthropometric proportions defined by Drillis and Contini, the system calculates a target camera height. With controlled geometry, the software estimates anatomical landmarks, calculates the angle in real time, and records the session to compare attempts and learn functional range of motion. On the computer, a Python backend runs using Flask, OpenCV, and MediPyPose, while camera positioning is executed through an embedded closed-loop system.
Processing is done frame by frame, depending on the exercise select. The system defines which articulations to analyze and which landmarks to use. MediPyPose detects 33 anatomical points per frame, approximately 30 times per second. With these points, we construct vectors between body segments and calculate the instantaneous angle using vector trigonometry, product point, and arccosine. The angle is transmitted in real time to the browser, while the session is logged in the database. Not a single value is taken, a stabilization window is applied. A smoothing by moving average at the room is calculated over the interest series, minimum, maximum, and functional range. Finally, that information is contrasted with normative range and automatically incorporated into the report. The didactic value is in the complete flow. The student sees the angle in real time, correct their executions, and in the end there is objective evidence to compare repetitions. The report is automatically generated in PDF and includes the room, its classification, and its average.
The system's mechanics were designed from scratch to maintain a stable and repeatable geometry. Each session begins with a homing process. A lower limit is which establishes the mechanical zero, and from there positioning is controlled in a closed loop. A DC motor with a gearbox integrated incremental encoder is used. The encoder reading is compared to a reference, and a proportional control adjusts the PWM based on the error. Vertical displacement is implemented with a two-belt and pulling system, guide along a profile to minimize tilting and ensure consistent image capture. The PWM and direction signals are generated from an Arduino Nano, and the power state is controlled with an L298N driver. Logic's level current margins and actual voltage drops of the system were verified. The PWM was set to 25 kHz to operate outside the audible range. In addition to the vertical axis, horizontal panning was incorporated to the center the articulation without manual readjustment. This axis is controlled by a servo motor and an ESP32 module via Bluetooth.
From a circuit and systems perspective, the project's main contribution is integration. closed-loop control to standardize capture, video signal processing to estimate angles, and an interface that turns all of this into a guided and recordable practice. The system operates in a two-dimensional plane to ensure repeatability and maintain a clear pedagogical focus. The session is started, the camera is positioned, the movement is performed, and the range of motion is obtained in real time. At the end, the report is supported with evidence of the practice. When the capture changes, students end up discussing the method. But when the capture is consistent and the calculation is automatic, the discussion shifts to what truly matters in biomechanics. What the range means, how it is interpreted, and how it changes between attempts. This is BioTrack's goal to transform classroom practice into hands-on, experiential learning, even in environments where no dedicated laboratory is available.